Okay, we have started recording and let's start the backup also. Okay, we are all set now. So we were discussing the thin wall pressure vessel on Monday, and we had discussed quite a few things, especially with regards to the case that that this was a situation of plane stress on the wall, even though it is a curved wall, both for the cylindrical pressure vessel as well as the spherical pressure vessel. And then we had talked about this condition of axis symmetry, and we had noted that the two formulas for stresses, the sigma 1 equal to PR by T that we obtained for the circumferential or the hoop stress, and the sigma 2 is equal to PR by twice T, which is for the longitudinal stress. Of course, the sigma 1 and sigma 2 we have for the cylindrical pressure vessel, and for the spherical pressure vessel we have only one stress, this PR by twice T. Now all of these things, they also happen to be the principal stresses, because on the planes on which we are considering those stresses to be acting, they do not contain or they do not show up any shear stresses. We had gone into some detailed discussion regarding this, and then I had mentioned in passing that it is possible to have very interesting problems in the context of pressure vessels, especially when we combine it with our previously learned concepts regarding the transformation of stresses, the transformation of strains, and everything. So the tutorial sheet, which is under preparation, I'll try to release it either today or tomorrow. And we are going to solve a few problems from that tutorial sheet, whatever has been prepared till now, in this class as well as in tomorrow's class. You will see that some of those problems combine a lot of concepts together. At the end of the previous class, that is Monday's class, I had posted a couple of questions in our discussion channels. So did you take a look at that? I had specifically asked about the component of the shear stresses which would be present here. So either on this plane or so suppose we consider this plane, this hatched plane, or perhaps this plane. What is the component of the shear stress which is actually 0? I had mentioned that tau r theta equal to 0. Okay, so first of all you answer me, this tau r theta, this is acting on which plane? Or on a plane which is perpendicular to which axis? The tau r theta, the shear stress that we had proved to be equal to 0 in our previous class from arguments of axis symmetry and symmetric loading. This tau r theta shear stress is acting on which plane? That is my question to you.
So the plane perpendicular to
the plane which is perpendicular to which axis? Can you please? I could not hear.
Plane perpendicular to cylindrical axis.
Cylindrical axis. What is cylindrical axis? You tell me in terms of r, theta, or z.
The plane perpendicular to z.
So this, who is saying this?
the plane perpendicular to r, sir.
Yes. The tau r theta, that is the shear stress which is occurring on the plane which is perpendicular to the r axis. Okay, so basically this plane, the tau r theta is on this plane, but we don't want that shear stress. I mean, it is good that it is 0, but in order for this sigma 2 to be equal to 0, which is the shear stress component that we want to be 0? For sigma 2 to be equal to the principal stress, What is the shear stress here?
The tau theta r.
So this is my question. Tau, sorry. This tau, some subscript is equal to 0 on this plane. Okay, so I'm talking about this kind of a shear stress. What is
tau
that?
theta.
What is tau theta? It has to be two subscripts, no?
Sir, I said tau theta r.
Tau theta what?
R, sir.
No. Tau r theta, this is occurring on this plane, on this one. So what is the axis which is perpendicular to this plane, this hatched plane?
X-axis.
It is the, so tell me in terms of the r theta z. So suppose the z is like this. Suppose, so this is, we have said that this is our x-axis and this is the y and this is the z. But suppose you imagine that this is the z-axis, the longitudinal axis is the z-axis, and perpendicular to this is the r-axis, and theta is like that. So in that sense,
It will be perpendicular to the z-axis.
yes. So what should be the first subscript? Shouldn't it be z?
Yes, sir. Z.
What will be the second one? What is this direction? Yes, that is why it is theta. So tau z theta equal to 0. That is, this is the shear stress in the hoop or the circumferential direction. Okay. Tell me about this one. What is this? Oh, well, the direction is wrong. This one. What is this axis perpendicular? What is this plane perpendicular to?
Theta. So theta axis.
Theta.
Axis. Okay. And what is the, so theta, and what is it along?
Z.
Yeah. So this is actually tau minus theta minus z, that kind of thing. So this is also equal to 0, which makes sense because tau z theta equal to 0, which implies that tau theta z equal to 0. Okay, so I'm emphasizing this because many times in many of the interviews and everything, people ask these things because in our textbooks, this is not clearly mentioned. Okay, so we always keep saying that these are the principal stresses and on those planes the shear stresses will be 0, but exactly which component of the shear stress are we talking about? That we must be absolutely clear. Okay, let us move on to problems now. There are a number of concepts here and there. I had mentioned in the previous class that there is a very important concept which has to do with the change in the dimensions of both the cylindrical and spherical pressure vessels, but I think it will be more straightforward if I just launch into the problems and then discuss those concepts in the context of those problems. Okay, so this is the first problem, slightly different kind of thing. I mean, it's basically a two-line problem, a two-line solution, but you note carefully the situation here. So we have a thin-walled cylinder which can be supported in one of two ways shown. So in the first case, the cylinder is standing on some flat platform. Okay, some floor it is standing. And in the second case, the cylinder is hanging from a wall. That is the two different situations that is being mentioned here. If the piston causes the internal pressure to be 0.6 megapascals, determine the state of stress in the wall of the cylinder for both cases. So this is the cylinder. What are the stresses which are generated there in both these cases? And the dimensions, of course, are given. Please note the dimensions here. Okay, the inner diameter of the cylinder is 250 mm and the wall has a thickness of 6 millimeters. So it whenever you are trying to apply the formula that sigma sigma 1 is equal to, so which one did I write as sigma 1? Yeah, so sigma 1 is equal to PR by T and sigma 2 is equal to PR by twice T. I always forget which one I write as sigma 1 and which one is sigma 2. So please note that we have this ratio of R by T, and these formulas are applicable only when R is much greater than T. Okay, please remember this. Now, this is certainly true here, that the radius, which is 125 millimeters here, the inner radius, that is significantly larger than this thickness of 6 millimeters. But what is the difference between these two situations? Who can tell me? This has nothing to do with stresses. I mean, the difference between the two things, it has nothing to do with stresses directly or anything. It's very basic mechanics thing.
So there will be normal stress in B.
There will be normal stress in B. What do you mean by normal stress?
So where the force is acting along the piston, the wall is there maybe.
So you mean in this direction, in the vertical direction?
Yeah, yes, sir.
Why do you think that will happen? Hello. Why do you think that will happen?
So actually, that the cylinder is attached to that upper ceiling, so that's
Yes.
why.
Right. So the situation is like this, that in this second case, if you consider this as the free body diagram, this is some force acting here, and this force will be balanced by the forces which are present all along the periphery here. Okay, as it is joined to the wall, to the ceiling. But in this particular case, the situation is like this, that you have the same kind of cylinder, but the externally applied force, is balanced by the reaction force from the floor or the platform which is beneath the cylinder. Okay, now in this case, you do not have the generation of any tension in this wall. In this wall, these vertical walls of the cylinder, you do not have the generation of any tension. But here, you certainly have the generation of the tension in these vertical walls. Which is why, in the first case, you will certainly have the presence of the sigma 1. This sigma 1 is along the hoop or the circumferential direction. Okay, this is the hoop or the circumferential direction, meaning that it is along this direction. Okay, all around the periphery. So this is PR by T. You can calculate this just by plugging in the values. P is given to us, radius is given to us, thickness is given to us. You plug in the values, you'll get this thing. But the sigma 2, which is the longitudinal direction means parallel to the walls. In part A, so this is part A and this is part B. This is actually equal to 0. You can see the answer also here. Okay. For the part B, sigma 1, it remains unchanged. This is PR by T. You can calculate this value, and sigma 2, that is the longitudinal stress, that will actually be calculated from the formula that we had derived. Okay, so whenever you encounter a pressure vessel like scenario, don't just blindly put down the values in these two stresses to obtain the answer. Okay, just pause for a couple of seconds to see what the situation is demanding you. Okay, that is the lesson, that is the moral of this question. Okay, Does anyone have any doubt from this? Because this is a purely conceptual kind of thing. Okay, had this been JEE, this would have been like a very small objective question. Does anyone have any doubt regarding this?
Sir, excuse me, sir.
Yes.
Sir, in case A, if we consider a cross section which is cutting the cylinder, as the way when we were deriving the formula for sigma 2.
Or the sigma 2. That means you want to cut it along this.
Yes, sir.
Like this.
Yes, sir. So
Yes.
if that's the case, the fluid pressure is balanced by normal force for the lower body and the force applied for the upper body, right? I mean,
Yes.
is that true?
Yes. Yes.
Okay, sir.
Yeah.
Thank you.
Yeah. That suppose we cut this body like in the case that we were deriving our formula, then the picture will look like this. So we take this cut, this orange cut, and we consider the free body diagram of the lower part. Then this force is still present from the ground below. What is this going to be balanced by? This is going to be balanced by the fluid pressure, which is like this. Okay, and correspondingly for the upper part, the counterpart of this fluid pressure, which will be acting upward on this part, that will be balancing this downward pointing external force. So it's very nice and consistent. Okay. All right. Moving on. This is the next question.
Sir,
Yes.
sir, could you please go back to the previous slide?
Yes.
I mean, here you had said that R greater than T. So these kind of approximations means in say suppose R is given to be 10,000 and say T is in the range of say 1 to 100 or like that, then we can say no greater than. But here 250 millimeter and it was 6 millimeter. So I mean.
In fact, these kinds of formulas will work even if R is, let's say, 10 times. So if it is something like R is greater than 10 times T, then also this is not too invalid. Okay, it is better if it is much more than this, but even if it is approximately just a little bit more than 10 times of T, then also this formula work pretty well. And okay, and it is good that you are talking in terms of orders of magnitude when you said like 10,000 versus 10 or 100. But please remember that these are actual dimensions. Okay, when you are saying 10,000, what do you mean by 10,000?
I mean, say in a question, it is given to be say where we have to make this kind of approximations, and say the radius is given to be say 10,000 millimeter, and we are working with say
10,000 millimeters means what? How many meters?
10 meters.
10 meter diameter pressure vessel is like pretty serious.
No, I'm not talking here about. I mean, only not in this situation. I mean, say in any kind of problem that we face. Say means. Yeah, where we have to take any kind of approximation.
I understand what you are coming from. Okay, so at your age, I also used to think like this, but try to understand that a real pressure vessel, it will be order. I mean, it can have a diameter of 1 meter, 2 meters, maybe a little bit more than that, but 10 meters is a little bit too big. Okay, so try to understand it like it's okay if you say like 1,000 meters, 1,000 millimeters or 2,000 millimeters. Versus, let's say 10 millimeters, 15 millimeters, usually these are the ranges. Okay, it is good that you can think like a physicist, but also develop your brain muscle to think in terms of an actual engineer who respects the kind of dimensions which are actually used in engineering practice. Okay, because I mean 3-4 years from now, you all will go into the professional world. And there in the actual industry, if you speak like that, it will not look good. Okay, you have to speak in real terms.
Okay, sir.
This is concerned, think in terms of orders of magnitude, all the sophisticated things you have learned. I appreciate that. If you go into higher studies, you will actually be expected to think in those terms, but your fundamental training has to be in the form of an engineer's training, okay? And there you have to respect these kinds of things. Okay. Yes. So as I told you, so some things, okay. So some real values, they should always be at the back of your mind. So when you are talking about Young's modulus, don't just arbitrarily say 10,000 GPa or something, because if you say something like that, it also has to be so that there is a material in the actual world which has such a high Young's modulus. Steel has a Young's modulus of 200 GPa. Don't forget that. Okay, aluminium is in the range of 70 GPa. Okay, some values, atmospheric pressure, density of water. I mean, like a table inside your head where you can compare with these kinds of values. Okay, get a feel of what is the force of 1 Newton. Okay, for those kinds of things, like you should develop you all are very good in maths, very good in physics, but at the same time, you should also develop a feel for these real values in the sense of comparing with real everyday experiences. For example, you guys, the boys, are maybe what, 60, 70, 80 kilos. Okay, you multiply that with the acceleration due to gravity, you will get some force. Okay, your weight in terms of some Newton. Now, you have a feeling about your weight, or if you try to lift your younger brother or sister, you have a feeling of their weight. Okay, like an actual real feeling of their weight. So try to compare that force, that feeling of the force of a weight, with the forces that you actually encounter in different problems. So sometimes it is written like 10 newtons or 300 newtons. How much does that 300 Newton compare with this kind of a force? Okay, that way you will get a real. Otherwise, you will never ever really get a feel of real engineering things. Okay, like an 800-ton vehicle or a 100-ton vehicle. What is the kind of difference? Those things really matter. Okay, let me stop lecturing and go on to the next problem.
Sir,
Yes.
Sir, I once come to the previous lecture, I had doubt in FBD of the second one, sir.
Yes. Tell me.
FBD of the second one, sir.
Yeah, tell me, what is the doubt?
Means I am getting into the zero, sir. Well,
What is getting to be zero?
Means if we take a section perpendicular to the longitudinal axis, sir.
Perpendicular to the longitudinal axis here.
Yes, sir. In the second case,
Yeah.
Means if you take FPD, there will be no force acting on the higher partner, sir, from below part. Means interaction force.
Please say that again.
If we take if we take the force on the upper part, there will no interaction between the, means it will be zero now, sir, because it will be balanced by the injury.
While it will be zero. So your diagram will be like this. What will be the fluid pressure here? It will be acting upwards. That must always be present, like this. Now you are saying that this is equal to this plus this. So this fluid pressure must necessarily be equal to zero.
Yes,
that
sir.
is what you are thinking, right?
Yes, sir.
Yeah, that is not true, because you understand that the lower part of this body, this is your diagram, no? Okay. So you will have a fluid pressure acting here also. So what will this fluid pressure be balancing? Tell me. Because that fluid pressure is always there. That's a physical truth. So that will be balanced by this force, the interaction force between the upper part of the cylinder and the lower. Consequently, you will have a non-zero force here. That is why, because of the presence of this force, that you are going to have a stress in the longitudinal direction, which is this sigma 2, because this is along the longitudinal direction.
Okay, sir. Okay, sir. Understood, sir. Thank you.
Okay. The 10-volt cylindrical pressure vessel shown in the figure is subjected to an internal gauge pressure of 15 megapascals. Very good. So please note the magnitude, okay, 15 megapascal. If the thickness is 10 millimeters and the material constants are Young's modulus equal to 200 GPa, nu equal to 0.3, determine the increase in both the diameter and the length of the pressure vessel. Please note that the radius of this, the inner radius of the pressure vessel is given to us as 0.5 meters. So the diameter is 1 meter. Again, 1 meter diameter. Okay, compare that with the thickness, 10 millimeters. So huge difference. So R by T is very much larger. So we are good with our formulas. But good with our formulas is one thing, but question is different here. Question is to determine the increase in both the diameter and the length of the pressure vessel. So it makes sense for us to try to think in terms of the deformations that this pressure vessel is undergoing, and that pressure, those deformations can be tracked if we connect the stresses which we can calculate directly from our formulas with the strains which we know from our generalized Hooke's law. So certainly you can go on to calculate your sigma 1 as well as sigma 2. That's direct application of the formulas. Both these things you can calculate, but then you have to connect these to the stresses, to the strains. How do you do that? Well, this is along the Hooke direction. Okay, so try to understand that. So let me write this. Hooke direction is epsilon theta theta. What will be epsilon theta theta? Tell me in terms of the generalized Hooke's law. 1 by E sigma theta theta. So sigma theta theta. Let me write this. Minus nu sigma RR plus sigma ZZ. Sigma theta theta is nothing but sigma 1. Sigma ZZ is nothing but sigma 2. This sigma 1 and this sigma 2. What is this sigma RR? Tell me.
So sigma RR is the pressure due to the fluid.
Very good. So sigma RR, strictly speaking, is actually P. Okay, sigma RR is actually P. Is it not? But you note that this P is actually much smaller than P into R by T, or even by PR by twice T. Why? Since R by T is much larger than 1. Which is why in practical purposes, in practical calculations, we take this sigma RR to be equal to 0. And please don't forget that we had actually alluded to this particular thing earlier, that we practically take this sigma RR to be 0, which is why it makes sense for us to consider this case like a plane stress case. Okay, so this thing is approximately equal to 0. Okay, which is why this is approximately a plane stress case, not a strictly plane stress case. So we know sigma 1, we know sigma 2, the value of Young's modulus and Poisson's ratio are given to us, so we know epsilon theta theta. Now epsilon theta theta in terms of the change in the dimensions of the pressure vessel, what is it? Who can tell me?
Sir, increase in the circumference.
Tell me in terms of the actual formula.
So 2 pi into delta R.
Yes, so it is 2 pi R plus delta R. This is the change in the circumference or the new circumference. This is the new circumference minus the old circumference, twice pi R divided by the old circumference. So see, again I am utilizing your high school formula. So new length minus old length divided by old length. So this is coming out as delta R by R. So determine the increase in both the diameter. Okay, so diameter change has been asked, so just you have found out the ratio between this thing, you can find out this also, no problem. Okay, so you know the value, because you know the value of sigma 1, sigma 2, E and nu, you know the value of this epsilon theta. You plug this value here, you can find out this twice of delta R or delta D you can find out. Okay, so this is basically delta D by D. Okay, so this basically means that delta D is equal to epsilon theta theta into D. D value is given to us as 1 meter. I want to point out something here, that I have seen your senior batch students do something like this, that whenever they encounter this epsilon theta theta, they don't think in terms of the circumference. What they do is they directly think in terms of the diameter, that I have been asked to find out the change in the dimension. I will just write epsilon is equal to delta D by D. You see, eventually epsilon is coming out to be delta D by D. That is fine. But even conceptually, they write this as delta D by D as if they are directly tracking the change in the diameter. This concept, like conceptually, this is wrong. Okay, when you proceed by this route, by tracking the change in the circumference, that is the correct route. Even though the formula is the same, but directly writing like this is completely wrong. It shows that you have not understood what you are doing. Because understand that epsilon theta theta is along the circumference. Okay, so you have to track the change in the length of the circumference. This is a very, very important concept. What about the change in the length? For that, what do I do? Which epsilon?
Sir, epsilon ZZ.
Yes. So epsilon ZZ. Now epsilon ZZ again in terms of the formulas will be what? Sigma formula for the generalized Hooke's law. This thing. This is approximately equal to 0. Sigma theta theta is sigma 1. Sigma ZZ is sigma 2. So you know how to find out epsilon ZZ. And then epsilon ZZ in terms of the change in dimensions will be what? So this will be L plus delta L
by L.
Yeah, minus L divided by L. So this is pretty straightforward. From here you can find out delta L is equal to epsilon ZZ times L. L is given to us as 3 meters. Okay, you see, I mean, these are typical dimensions of a pressure vessel, very, very typical dimensions of a pressure vessel. Okay, so you can find out this value. That's it. Finished.
Excuse me, sir.
So, yeah, tell me.
So actually you told that epsilon theta theta is like changing circumference. So suppose if we have to find the epsilon RR, then we can directly put delta R by R or like delta D by D.
Absolutely.
Okay, sir.
Okay. So a thin-walled spherical pressure vessel having an inner radius of R and thickness T is subjected to an internal pressure P. Show that the increase in the volume within the vessel is this thing. So they are asking about the change in the volume. And use a small strain analysis, you will see what that thing is. So it's a very general theoretical kind of problem. So given the pressure and radius, inner radius and the thickness, you can find out the sigma 1. And this is a spherical pressure vessel. So it doesn't make sense to distinguish between sigma 1 and sigma 2. There is only one sigma, which is PR by twice T. This we can find out. I mean, if this question had been asked in terms of numbers, you would have been actually been able to find out the numerical value of sigma. All right. Now, for the change in the volume, what do we need? So, volume for a sphere is what? 4 by 3 pi r cube. Is it not? 4 by 3 pi r cube. All right. What will be V plus delta V? It will be 4 by 3 pi r plus delta r cube. Now let us take this r out of this thing. So now we are again going to work like a physicist. Now we have to use a small strain analysis. So you can very well properly expect that delta R by R is going to be very small. This is going to be very small, which means you can expand this and neglect higher order terms to obtain so what will be this thing up to the second term?
4 pi r square delta r.
No, just tell me this thing. 1 plus delta R by R cube.
1
1
plus
plus 3 delta R by R.
Yeah. Okay, so this is not actually equal to, rather this is approximately equal to. So this is our thing. Now delta V, that means, so V is this 4 by 3 pi r cube. So delta V will be how much? 4 by 3 pi r cube times 3 delta R by R. Okay. Now this delta R by R, where can you obtain it from?
So generalized Hooke's law.
Generalized Hooke's law. So we can use our epsilon theta theta. So epsilon theta theta is what? Tell me. Generally, you tell me.
So 1 by E.
Yes.
Sigma theta theta minus
Sigma theta theta minus
Poisson ratio times mu
times
the sigma RR and sigma ZZ.
No, that is why I asked. Think again and say, what is Z here? This is spherical pressure vessel, man. Why are you using cylindrical coordinate system? This is a spherical pressure vessel, so use a spherical coordinate system, no? So in a spherical coordinate system, what are the coordinate axes? Or what are the coordinate variables?
R theta phi.
R theta phi. So this should be like this. So don't forget your first year maths, okay? What first year maths? You know this from your high school physics also. So now you tell me, what is this sigma RR? Sigma RR is again equal to P. Actually it is equal to minus P, but fine. So this is going to be approximately equal to 0. What is the sigma theta theta and sigma phi phi? You see, whenever you are talking about a spherical pressure vessel or any sphere, okay, any sphere on which you have a perfectly symmetrical kind of loading all around. Perfectly symmetrical means it is perfectly spherically symmetric. There is absolutely no distinction between any radial direction. Then you can easily understand that there is no distinction between the theta direction and the phi direction. So usually we write things like this, no? That this is your R, this is your theta, this is your phi, things like that. This is theta, this is phi, or some other way. So there is no distinction between this theta and phi. That is why this sigma theta theta is sigma, this sigma phi phi is phi, sigma. Okay, that is why there is no sigma 1 and sigma 2 here. It's the same thing here. So this one comes out like this. Now epsilon theta theta is again equal to your change in the radius, your change in the circumference so you have your formula for this delta R by R, which is what you need here. So delta R by R is going to be equal to sigma into 1 minus nu by E. And sigma, you know the formula for this PR by twice T. Just substitute the values properly here, we'll get the answer. Okay.
Hello.
Yes.
Yes, sir. Can you just explain it why sigma RR was 0? If sigma theta theta and sigma phi phi exist, why not sigma R? I mean,
So the argument is like this, that you actually calculate the real values of PR by T. R by T is, if you go up in this thing, okay, put the actual value of R here. What is this R? 0.5 meters. Okay. And T is what? Where is T? Thickness is 10 millimeters. 10 millimeters means 0.01. What is this value? This is 50. Is it not?
yes, sir. Yes.
Yeah. So what, as I said earlier, that if R by T is greater than 10, it works very well. These kinds of things. Here you are having R by T is equal to 50. Okay.
Yes, sir.
So in terms of the orders of magnitude, there is a 2 orders of magnitude difference between the value of sigma 1 or sigma 2 with the sigma RR value. Okay. You will get this thing as P, and if you really want, you can avoid all of these approximations, do a full elasticity analysis, but at the end of the day, the accuracy that you obtain, the accuracy in your answers that you obtain by using this kind of an approximate solution based on the assumption, on the simplifying assumption that sigma RR is almost equal to 0, and a full elasticity solution by taking sigma RR equal to P, there is not much difference in the accuracy. Okay, so that is why we do this from a very practical consideration. Okay, it is possible to do various kinds of sophisticated maths and get the solution, but I mean, what is the benefit? What is the real benefit in terms of the accuracy that you are obtaining? Okay, as I said earlier, that see, any decent mathematician can give you a very sophisticated formula, a very sophisticated theory, but it is only a very, very brilliant mathematician who can work with an approximate theory but still tell you in which range of physical values those approximate theories still hold up, because it is much easier in the actual engineering field to work with these kinds of simplified formulas and everything to get a quick calculation and a design basis. All right. Okay, next question is this. We have a special kind of arrangement here again. So air is pumped into the steel thin-walled pressure vessel at sea. So this is a thin-walled pressure vessel, and there is some kind of an input nozzle, and air is pumped into this pressure vessel through this arrangement. Inner radius and all this thickness and everything is given. Again, you see the difference between them. Okay, 40 times. Again, steel, 200 GPa, Young's modulus, nu is equal to 0.3. Now, there are two parts to the question. In the first part, it is given to us that if the ends of the vessel are closed using 2 pistons, so this is one piston and this is another piston. They are connected by a rod AB. Determine the increase in the diameter of the pressure vessel when the internal gauge pressure is 5 MPa. So the situation is like this, that air is going into this steel pressure vessel, but because of the presence of these 2 pistons, the air is trapped between these 2 pistons. It cannot go beyond these 2 pistons. Okay, so the pressure vessel effectively is this piston plus this piston plus this curved wall. So it is this part which is the actual active zone. This is our pressure vessel. But this is the kind of pressure vessel where you have these 2 rigid ends. Okay, so what is the implication of this? in terms of determining the stresses. You have to again think directly from a very basic mechanics point of view. What is the implication of having these two rigid pistons at the two ends? As far as the determination of the stresses are concerned, it has a certain implication. Tell me, what is it?
So stress is also created in AB as mentioned in the problem.
Stress is also created in AB. What do you mean?
It's a normal stress in AB rod.
They're in the rod connecting the two pistons.
I mean, that is great. That is the given question. Of course, it is there. But in terms of the stresses which are generated in this pressure vessel, this modified pressure vessel or effective pressure vessel that we are considering here, marked out by these red lines, what is the implication in terms of the stresses? Like you see, in a pressure vessel, cylindrical pressure vessel, you have sigma 1 and sigma 2 as your formulas. Will both those formulas be activated?
Sir, I think no, we should consider a cross section and we should maintain the forces in the longitudinal direction.
Actually, in the longitudinal direction, do you think there will be any forces?
I think sigma z will be 0.
Sir, in AB also there is.
Sorry?
So to identify the stress in AB, we need to consider the balance in
Yeah,
longitudinal.
that is fine. That is fine. That is fine. But what I'm asking is like this. Okay, maybe my question was not clear. You have this thing, right? This is the thin wall pressure vessel. This is the steel. And you have the piston here. You have the piston here. Okay. And the fluid pressure is acting on this thing. The fluid pressure is acting on this thing. My question is that, do you think there will be any longitudinal stress in these thin walls of the pressure vessel?
No, sir.
That is my question. Okay. So there is no doubt that on this curved wall, you will definitely have the sigma 2. Okay, so if you consider a little element like this, then there is no doubt that you will definitely have the sigma. This is not sigma 2, sorry. This is sigma 1. I always make this mistake. This is sigma 1, the hoop stress. But my question was, will you have any sigma 2? Sigma 1 is definitely PR by T. But what about sigma 2? Sigma 2 is actually going to be equal to 0 because the responsibility of this longitudinal direction is completely taken over by these two pistons, not by the longitudinal direction of this steel vessel. Okay, so fine, we can find out the hoop stress PR by T. You will get something, but and from that you can also find out the increase in the diameter of the pressure vessel. Okay, so sigma 2 is equal to 0. Increase in the diameter of the pressure vessel, we have seen that you can obtain it from epsilon theta theta is equal to 1 by E sigma theta theta minus nu sigma RR plus sigma ZZ. So I'm attempting this part. Okay, determine the increase in the diameter of the pressure vessel. That is what I'm trying to do here. Sigma theta theta is sigma 1, sigma ZZ is sigma 2, but that is equal to 0, and sigma R is approximately equal to 0. So you can find out this epsilon theta theta, and again epsilon theta theta is equal to twice pi R plus delta R minus twice pi R divided by twice pi R. So this is equal to delta R by R, and this is equal to delta D by D. So when you know this epsilon theta theta, you can find out the delta D, the change in the diameter of the pressure vessel. Okay, this you can find out. For the second part, for this thing, what is the tensile stress in the rod AB? What do you do?
Sir, excuse me, sir.
Yeah.
Sir, I'm not getting a clear idea why sigma 2 is 0. Is that because the piston AB is not physically welded to the outer cylinder, or?
Yes, 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 that is the thing.
Okay, okay, sir. Thank you, sir.
Yeah. So good question. So the reason why we are saying this sigma 2 equal to 0 is that even though these two pistons are touching this thing, touching in the sense that it is not allowing any fluid or this any of this air to escape through this gap, but it is not welded or bolted to this pressure vessel ends. Okay, unlike these two ends where it is actually welded here. Okay, so there is no physical adhesion between these two things. Okay, tell me what do I do for this tensile stress in the rod AB?
So we can find the force in that rod AB by normal FBD.
Yes, you can find out the force in the rod AB. So why don't we do something like this? Let us consider a cut section of this thing. We cut it like this. Okay, and consider the free body diagram of that right hand side portion. The fluid pressure is acting like this. This is the pressure P. This entire inner radius is given to us. The diameter of this connecting rod is also given to us. What is the diameter? If it has a diameter of 100 millimeters, okay, good. So now you tell me what should be the force that is present on this thing?
P times area of the circular disc.
Be very careful. What is the actual fluid acting on which area?
So total area minus the area.
Total area minus the area of that rod. Okay, so this force. So this force will be equal to P, which is the fluid pressure, times pi. Let's say this is pi r square minus pi this. I need some different name for this. Okay. Rod, let's say r rod. Okay, this is the thing. And F, from F you can obtain the tensile stress. So sigma tensile is equal to F divided by pi rod square. That's it. Okay, you know all the dimensions here, all the values here. You can find out F, and you know this also, you can find out sigma T. That's it. Next part is interesting. If the distance, yes, there was some.
So actually in part A we have asked that determine the increase in diameter. So can we not directly do the formula like sigma RR is equal to 1 by in bracket sigma R minus mu, like that?
Use epsilon RR, that one.
Yes, sir. Epsilon RR equal to 1 by.
Try that, see if it matches or not.
Okay, sir.
I have not done it myself. Okay, you check it and ask if there is any mismatch. We can investigate what is going on, or if it is matching, we'll be very happy. All right, for this part B, it is given that if the pistons in the part A of the question are replaced by the walls connected to the ends of the vessel, determine the increase in the diameter of the pressure vessel. Okay, so basically what is done is in this part B, these pistons are removed. If these pistons are removed, then it is like a very standard pressure vessel, where you have the two ends which are actually welded to these curved walls. Okay, and then it's a very standard kind of thing that you have to do. Okay, which you have been doing in the previous problems. So part B you do yourself. Okay, so I hope there will be no problem here, because when you're doing part B, then you will have to consider very much a non-zero value of sigma 2. Okay, the longitudinal stress that will come out as PR by twice T, not very much non-zero. All right. Okay. Now, so this is a different kind of problem. There is no business of pressure vessel here. Okay, why are we doing this thing suddenly? So you take a look at this thing. So we are in this chapter now, miscellaneous applications. This is the first part, the thin walled pressure vessels, whose theory we have discussed, and a couple of problems we have discussed. And there are more problems on thin walled pressure vessels in the tutorial sheet. You can try that. Now, there is this topic, thick walled pressure vessels. I have written this as may be dropped. In all likelihood, this will not be dropped. Okay, we have dropped many things earlier, but this thing will not be dropped. Principal stresses in a beam, that we will cover later, but this fourth topic, stresses under combined loads. Now this is an extremely important and interesting topic because it covers within it almost everything that you have covered till now, including thin walled pressure vessels. Meaning that there can, so earlier what we have done is that individually we have studied torsion of various kinds of shafts, of course circular shafts, but in various kinds of situations. Then we went on to the study of beams, where we did these kinds of calculations regarding bending moment and shear force. And then we went on to the flexure from which appear in the cross section of a beam as a result of the bending. So this was referred to as the bending stress or the flexural stress. But please note that when we were doing this, we completely neglected any effect that torsion might also have in those kinds of situations. Next, we moved on to shear in beams. And when we were talking about shear in beams, we were talking only about shear in beams. Then we were not thinking so much, maybe we were thinking a little bit about the flexure, but we were not thinking certainly about torsion. So these things we have studied quite separately from each other. And then this was a very general kind of discussion over 2 weeks, transformation of stresses and strains, very general notions of changing our coordinate system, oblique orientations, this and that, principal stresses, principal strains, all these things we have covered. So all these things that we have covered till now have been quite separately done. This is the part, the stresses under combined loads is the topic which will bring in all the things together. For instance, we can cover problems which will involve the shearing stresses, not just due to bending as you have studied here, but also shear stresses which arise because of torsion. Because you remember that in torsion, the kind of stresses which you calculated using the formula TR by J, that was a shear stress. In the shear of beams also, you ended up calculating the tau XY in beams or tau XZ in beams. Okay, so there is a possibility that the shear due to torsion in a particularly complicated situation means a very complicated loading kind of situation, you can have torsion arising together with shear due to bending. So these shear stresses may have to be added up together. Similarly, in your first year, you studied a little bit about axial stresses directly. So if you have a force, if you have a area, so if the force is acting normal to the area, so the normal stress is F by A. Nothing can be easier than that. Of course, that is this, the average normal stress, but you know the implications of that. Now, this bending stress or flexural stress, that is also a normal stress. So it is possible that you may have a situation where you have not only bending in a beam, but also some kind of normal force acting on the beam. In that case, the normal stress due to bending has to be added up or subtracted depending on the sign from this or with this or from this normal stress due to axial forces. So very interesting situations may emerge when you have a real complicated loading scenario on a simple beam structure or beam-like structures, and we wish how these things can be calculated. Okay, towards that end, so there is no theory here. Okay, so stresses under combined loads, there is no theory here. You just have the applications of the various things which you have been learning till now. Okay, there is no new formula or anything. It's just combining different formulas in appropriate scenarios. That is why I have given you this problem, and there can be innumerable other such problems. Okay, so look at this question. We have a drill, and this drill is jammed in the wall and is subjected to the torque and force as shown. So maybe it will be not so clear because it's a small diagram. Let me just make it bigger. You see, there is a torque here. Okay, you have this torque here, 20 Newton meter. And you also have a force being exerted on this overall drill, which is certainly being transmitted to this drill bit because of the application of the force from the person's hand or the user's hand. This force is being acted upon in an oblique sense. This ratio is given, this 3, 4, 5 means this vertical side is 3, this horizontal side is 4. So it's a nice right angle thing. You can obtain the cos theta and sin theta business from here. All right. Now, without going into any calculation or anything, you tell me by looking at this drill bit. So our focus will be this drill bit. Why it will be the focus? It will be the focus because we have been asked to determine the state of stress at the points A and B on the cross section of the drill bit at section AA. I don't know if you can see this clearly or not. The AA is here. Okay, this is our AA. This is AA. Let me just make it bold. This is AA section. So just at the tip of this drill bit, you have the section AA. And if you look at it from the YZ plane, so you see this is the X plane and this is the Y plane. If you look at it into the X-axis, that is, you look into the YZ plane, the drill bit will look like this circular cross section. Okay, and we have been asked to determine the stresses at the points A and B. So we are going to take a couple of minutes break now. But think, what are the kinds of stresses that are going to show up? Okay, and if possible, try not to look at the answers, which will give away the hints towards what you have to think about. Just try to think in very general terms, what kind of normal stresses and shear stresses may be appearing and due to which kind of forces. We'll come back to this discussion and we'll spend considerable amount of time trying to solve this. Okay, it's a very, very important problem. So we take a couple of minutes break and then we'll start discussing again. All right, so we resume our discussions now. So have you thought about it? What kind of stresses, which loading will create what kind of stresses? Any ideas? First of all, think about the easiest kind of stress, the normal stress, which will be generated in this x direction. What will it be due to?
Sir, it will be due to bending moment.
Please say that again.
Sir, it will be due to bending moment. I mean, we will draw the bending moment diagram.
Okay.
From flexure formula, we can get the sigma xx at
But that is due to which force?
150 Newton.
150 Newton, but which component of it?
So
See,
the vertical component.
the vertical component, and the horizontal component will not exert, will not induce any moment there.
No, sir. The vertical component induce a moment for A, and the horizontal component is responsible for the sigma xx in B.
Okay, okay. Any other opinions, comments before we actually launch into the solution of this problem? Okay, no, normal stress is probably everyone can think about. Who can tell me something about shear stresses? Because of what reasons shear stresses are being generated?
The vertical force due to wall.
Vertical force due to wall, and that vertical force due to wall is being induced due to which force?
150, 150 newtons vertical component.
150 Newton vertical component of that. Okay. Anything else?
Sir, if there is friction, we will have force, but like is the friction?
Reaction force is appearing on the drill bit is because of the entire interaction of the drill bit with the wall, which very much includes within it the effect from friction. So that is not something different. Look at the diagram. Any other loading is given on the entire drill and the drill bit?
So due to torsion.
Reaction moment is even 20 Newton meter.
Look at this. 20 Newton meter torque is also given. Okay, so on the drill bit, on this red highlighted portion of the drill bit, there is a 20 Newton meter torque also. Do you not think that some shear stresses should be generated due to the presence of this torque? Because this is a torsion like scenario.
Yes, sir, it will generate a shear stress.
Yes. So your drill bit, if you just zoom into that red colored portion, it will look like this. And this end of the drill bit, which is just adjacent to the wall, that is where the section AA has been taken. So this cross section, this circular cross section that you are seeing, that is basically this end. So this is the drill bit. All right. Now it is time to actually solve this problem. You have thought about it a little bit. And these things are quite separate, so I'll just remove this. I need a little bit more space. Okay. So first order of business is to properly find out the various forces which will be acting at this section. Okay, so what do you suggest I do? See, the questions which I am asking you, you all know the answers. Like you are officially expected to know the answers because we have covered those relevant areas, starting from your first year basic engineering mechanics. So my question to you, right, first of all, first and foremost, before we go into the calculation of any normal stresses or shear stresses, we have to find out the actual vertical component of the force, the horizontal component of the force, the various bending moments and everything. How do we go about doing that?
So first we translate the 150 Newton force onto the rod.
Okay, so in terms of equations, what do you do? Very specifically.
So we take the bending moment at the wall, and that will be equal to the moment exerted by the 150 Newton force.
All right. So what I'm basically asking you is this. See, in your first year basic engineering mechanics, you covered two chapters. One of them was 2D equilibrium, both under statics. Okay, in the first part of basic engineering mechanics, before any consideration of stresses, strains, all those things happened, you covered that's force and its applications. Then you covered 2D equilibrium. Then you covered 3D equilibrium. I was talking in those terms. Okay, so this is very much, of course, there are three-dimensional implications of that also, because we have to respect the Z axis also. But in terms of the solution of the forces and the resolution of the forces and the moments, this is a two-dimensional equilibrium problem. And the two-dimensional equilibrium problem, what are the equations that we have to use? The static equilibrium equations. What are the static equilibrium equations? Tell me.
Sigma fx equal to 0.
Sigma fx equal to 0, sigma fy equal to 0, and sigma m of suitably chosen axis to be equal to 0. Alternatively, that is not just the only set of equations which you will have to follow. Depending on the situation, you may also have to try maybe one force balance and two moment balances, something like that. Okay, so keep an open mind about it. Of course, in this particular problem, it will be enough for us to consider the very standard set of equations: sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. Okay, so we'll do that. First of all, sigma fx equal to 0, the force balance along the x direction. Now, just writing an equation like this without drawing any free body diagram is a crime against mechanics. So we must draw a free body diagram also. This is our drill bit. Very rough kind of free body diagram, but in free body diagram nonetheless. I'm not going to be very faithful to this outline. You just try to understand what I'm trying to. I think this is decent enough. Okay. There is some force here. Okay, this is the 150 Newton force. This is our x-axis, because in a free body diagram, we must always respect the x-axis. I mean the coordinate axis. These are the x and y. Now, the z-axis is pointing out of the screen or into the screen, because into the screen, because usually we consider a right-handed coordinate system. Okay, so our z-axis will be pointed into the screen, represented by this cross mark, as if an arrow is going into the screen. Okay. Now, with this picture in mind, you tell me what are the forces here. So I will have one vertical force here, which is Vy. Okay, I will have one horizontal force here, which is, let's say, Nx. Anything else that I'm missing?
Moment.
What about, okay, moment, but in terms of external loading, torque, that is also loading, right? External loading. This is the torque. This is the force P. Values of this are known. You were telling about moment. So if I want to represent the moment about the z-axis, I can represent it like this. Let's say this is mz. Anything else that should be here?
So reaction in Z.
Reaction in? I could not hear you.
So along Z axis reaction.
Reaction along z-axis, Vz. But you see, there is no force. I mean, sure, you can have a Vz, no problem, but Vz will turn out to be actually 0. But there is something which you have not considered till now. What about moment about the x-axis? Because you see, so you will need to apply a moment balance in the x direction also. That is something which you do not consider within the scope of your first year 2D equilibrium. That's a separate thing, but you still have to consider that. So in that sense, this is closer, or this is something in between a 2D equilibrium and a 3D equilibrium. So there will be a torque or a moment. Okay. So what will be the direction of that? Like this.
Opposite to T.
Of course, it will be opposite to T, but I want to draw it in the sense that it will give a positive sense in terms of the x-axis that we have chosen. So if I take it in this kind of a sense, then the Tx will be pointing, like if I curl my fingers along the Tx, then my thumb will be pointing in the positive x direction. So Tx will come out to be equal to minus T. We know that, but let it be so. Now, sigma fx equal to 0, what is it going to give me? Tell me.
Sir, nx.
Okay, nx. Tell me the equation.
Nx plus P
Plus
times
150.
Yeah, nx plus 150 times what?
So 4 by 5.
Into 4 by 5.
Times 4 by equal to 0. So nx is coming out to be how much? Minus 120 Newton. So we have taken the sense of nx to be this left hand side. It is coming out with a negative sign, meaning that the actual real force nx will be in the negative x direction. Remember that. That will have an important consequence later on in terms of whether the normal stresses due to nx will be tensile or compressive. Next, sigma fy equal to 0. Tell me what is it?
So Ny equal to minus 90.
What? Vy.
Yes, we were sorry.
Yeah. Vy is equal plus 150 times 3 by 5 Newton equal to 0. Anything else that I have missed perhaps? I don't think so. Okay, this is fine. So this Vy is going to be equal to next moment balance about the z axis. Because I have considered this variable mz, this unknown variable mz as that with that notation, I will write that with a m dash, okay, just to separate out the two things there, so that there is no confusion. So the moment balance about the z-axis, that will give me what? First of all, mz itself. Then tell me carefully. what will be the moment? What will be the moment due to the horizontal component of the 150 Newton force?
So 150 into 3 by 5 into 125.
No, horizontal component of
So
150.
into 4 by 5 into
Yeah. 4 by 5 into what?
125 mm. 0.2.
Yeah. So the moment, so if you consider the horizontal component, it will be along this line of action, this horizontal line of action, and that line of action will be at a distance of 125 millimeters from here. So this is Newton. This is 0.125 meters. Now tell me whether this is negative or positive.
Positive.
This will be positive because this will be oriented
Along positive Z.
to the component of. First, tell me the moment arm for this, for the vertical component.
0.4.
0.4 meters. Now, this is having a positive sense or negative sense? Negative.
The negative, sir.
Negative. This is equal to 0. So, do this calculation quickly and tell me the value of mz in terms of Newton meter.
So it will be 21.
Perfectly 21.
Yes, sir.
Yes, sir.
21 Newton meter. All right. Okay. So we have found out all these things. What are we missing till now? We have not written this thing, but let's do this. Sigma m dash x equal to 0. So we are trying to do a moment balance about the x-axis. This will be what? Tx plus 20 Newton meter equal to 0. This will give us Tx equal to minus 20 Newton meter. Okay. Now we go to the next page. Okay, I have created the new page in the proper place. I think it will be better if I keep on referring to this diagram and copy it from here. Keep this here. Okay. All this we have found out. Now we want to find out all the stresses corresponding to the point A that you see here on this cross. Okay, in your hand you now have the values of all the forces and the moments, torques, everything. Slowly we'll try to do the stresses. First of all, let us try to do the normal stresses. Okay, the normal stresses at A. Okay, so you try to think of it like this, that we are drawing our drill bit here. This is, let me draw this bigger. Why do I? Something like this, okay? Very zoomed in view of the drill bit. This is the cross section and we are interested at this topmost point A. This is our point of consideration, okay? So here you try to think how the normal stresses will be generated and as a result of these various combinations of forces. Yeah, this is better, okay? You refer to this diagram and refer to all these things that are present and tell me. Forget about the sign, just tell me the things which are the source of the stresses. We'll put the signs properly afterwards.
Sir, NX
NX, okay, NX.
and MZ.
Nx divided by the area of the cross section. Area of the cross section is very easy to understand. Okay. Okay, and what else? Due to Mz.
Yes, sir.
Mz. Yes, Mz. So that will be the flexural stress. So Mz times what? So you're basically thinking in terms of the formula that My by I. Okay, forget the plus or minus. We'll put that thing through a proper physical consideration. Mz y by I. So what is the value of the y?
So it will be the radius of the.
It is the radius itself. And there will be a proper I for this. Okay, devil is always in the details. Okay. So when you are considering the flexure of this kind of a drill bit, which you are now imagining in terms of its behavior like a beam of circular cross section, then your I will be calculated about this axis, because it is about that axis that the bending is taking place. Okay, because do not forget that your M is like this, your MZ is like this. Okay. What is the I about that? Tell me.
So pi by 4 into r to the power of 4.
Pi by 4 into r to the power 4. Very good. What will be the value of the polar moment of inertia? Because that also will require later. Let me write this down together.
So twice of I.
Twice of I. So pi by 2 r to the power 4. Okay. So I we know, R value we know, MZ we have calculated in the previous page. NX also we have calculated in the previous page. A is simply pi r square. So in terms of the actual calculations, we are good, but we are not yet done because we have to be careful with the signs. Now, ideally, all of these things can be done in a purely vectorial fashion, where you don't have to go about marking out what is negative, what is positive from physical considerations or geometrical considerations, but you are just starting out, and I think in terms of your learning, it will be good practice for you to think about these problems in a very physical way, like which bending moment is causing what kind of bending, whether it is upward kind of bending or downward kind of bending, which point is undergoing tension, which point is undergoing compression. If you think about these things in detail, you will develop your brain muscle towards getting a very clear-cut insight into these kinds of situations. It's a good practice to develop. Okay. So you tell me that MZ value was coming out as 21 Newton meter. But remember that the MZ was oriented like this. With a positive MZ, this is the thing. So what do you think the point A will be under? Whether it will be under tensile stress or under compressive stress due to this flexure MZ or due to this bending moment MZ?
Compression.
Compression. Okay. So if it is compression, we will put here a negative sign, and we will put this as with an absolute value. It is not necessary because MZ itself is positive 21 Newton meter, but it is good practice to do this just so that you tell yourself that you are taking all of these things, for all of these formulas like a direct formula without respecting the plus or minus sign from the formula itself. Rather, you are utilizing the negative sign or positive sign from a physical consideration. Okay, so very explicit, open source kind of doing the problem. Okay. Next, for this NX by A, you look at the sign of NX. What is this? NX was taken to be along the positive x-axis. Positive x-axis is along from right to left. but this is with a negative sign, which means physically the axial force is acting from left to right. If it is acting from left to right, then considering the point A, what do you think will be the effect in terms of the stresses, whether it will be tensile or compressive?
Compressive.
Compressive.
So here also we put a negative sign and put the modulus here. And this is where the modulus actually makes sense. Okay. So everything is known. You calculate this value, you will get something. This will be a compressive stress. Okay. So everything is very explicitly written. Within the bracket, we write this as compressive. Okay. So much about the normal stresses. Next for the shear stress. Okay. First of all, you tell me about tau xy. So we want to find out the tau xy at A. Remember, our x-axis is like this, our y-axis is like this.
So we
And
use
Z-
shear stress formula.
wait. Let me draw. Yeah, tell me now.
So we use the shear stress formula.
We will use the shear stress formula. Very good. What is the shear stress formula without any plus minus anything? You tell me.
So VQ by IT.
VQ by IT. Okay. Question now is that you have in your hand this formula. No, sorry, not this variable value. Okay, Vy. Fine. So Vy will be acting. So let's write this. Okay. Like a small child, we will write directly the formula Vy. Now, when you write the Q, this Q is about which axis?
Sir, about z-axis.
Yes. When you write the I, this is about which axis?
So same about neutral axis, about z.
Yes, about the Z axis. Okay. And T. What is the value of the T here?
Or
No.
Diameter.
See, we are talking about the point A, which is at the very top of the cross section. You see here?
oh, it should be 0. Since
Exactly, it should be 0. Okay, so suppose we had been asked to find out the shear stress at some point here. Then our our area of consideration would have been this. Had our point been here, like it has been asked in the second part, for the part B, then the area under consideration would have been the entire top semicircle. But here our point of consideration is the point A, which is sitting at the top of the cross section. So none of these things matter. Okay, we are at the top of the cross section. At the top of the cross section, the thickness under consideration is 0. The value of the QZ is also 0. Okay, so this is 0 by 0 limit. I mean, if you think in those kinds of mathematical terms, you will go mad. So the reason we don't do it like this is that actually this tau xy, it is following from the force. From the force value, the shear flow value is coming from tau xy times t. That is Vy qz by Iz. Because the qz is equal to 0, you don't even have to go into the calculation of the tau xy. Okay. So we don't write like this, all of these things. Rather, we understand that none of these things matter because this is going to be actually equal to 0. Tau xy is actually 0 because we are considering a point at the top of the cross section. Now, let us not forget that the shear stresses under consideration here are certainly due to the transverse force. Transverse force means Vy. But there is also another source of shear, which is the torsion. Now see, at the top of this cross section A, what is the direction of the shear stress due to the torsion? Remember that the torsion is acting in such a way that if you curl your fingers in the torsion sense, then your thumb will be pointing along the negative x direction. The reason here is your Tx is coming out to be minus 20 Newton meter. The Tx sense you took it such that your thumb was pointing in the positive x direction, that is coming out as negative. So physically, the torsion that you will be experiencing at this cross section will be pointed along the negative x direction. But the shear stress due to the torsion at the point A, which direction do you think it will be? Forget about formula or anything, okay? Just the shear stress at the point A due to the torsion, which direction will it be?
So outside the plane.
I could not hear you.
So out to the plane.
No, you tell me along positive z axis, along negative z axis, positive y axis,
Positive
negative
Z.
y axis, which one?
Positive Z.
The positive Z.
Positive z axis. Very good. Okay, so your shear stress here will be like this, in this direction. Okay, this is the direction of the shear. Now here we are talking about tau xy. Does that shear contribute anything in the y direction? It does not. Okay, so this is this zero that we have written, that is actually true. All right. Next, what do we do? We consider the tau xz at the point A. Now at the point in the z direction, we have only the contribution due to the what? The torsion. What is that? That is TR by J. And this is along the z direction, so we are good. We don't have to do any positive or negative. This is very much positive. Okay, if you want, you can write this as positive. If you want, you can write this also. Okay, and you just put the values. J you have calculated, R you know, Tx you have already calculated. So this is it. Okay, for the point A, nothing else. But now let's go to the point B, where it will help you to clarify your thoughts again. So we repeat this process. Put it here. Let me draw this again. This is our B, okay? You see this B is towards that other side, so this is B. Now we are not going to consider this A. Okay. First of all, sigma B. Tell me.
Sir, only due to nx by A.
Only due to nx by A. Why not due to mz?
Or it's 0.
Yes. So you can try to think of mz y by iz for the point B, but the distance of the point B from the z axis denoted by this y, that is 0. Okay, so this thing doesn't contribute. You have only due to nx by A. Now nx had a negative sign, So this is in the negative direction, this is compressive. So much about the normal stress. But the shear stress will be interesting. Tau xy. Tell me what is it. Please be careful, okay?
Sir, tau xy is due to torque.
First you want to write due to torque, okay? Let's write due to torque. Tau x Tx times R by J. Now this is along the positive y-axis or the negative y-axis?
Sir, negative y-axis.
Why it is along the negative y-axis? Because our tell me.
Positive y-axis, I think.
Tell me clearly. What is it? Positive, negative, which one?
So positive.
Along the positive y-axis. Tell me the
Yes.
reason. Tell me the reason.
So actually the torque at B will be along positive y-axis if we are taking the torque along minus x, then
If the sense of the torque is along the minus x, then it is, so looking at this cross section, like this, directly along this thing, our torque is appearing how? Like this. So at this point, which is the point B, the shear stress will be like this, upward. In that sense, it is positive. But we'll have to be a little bit careful about this. Next, tell me if there is any contribution due to the shear from the Vy. First, without sign, you write. Tell me.
Sir, excuse me, sir.
Yes.
Sir, for considering the shear stress due to torque in A, then it would be along negative Z, right?
Yeah, it will be negative.
Yes, sir.
Yeah, it will be negative. You are right. It should be along the negative Z. Because it is the same sense, no? Okay. Tell me. Tell me the contribution to the tau xy shear stress due to the Vy.
Sir, it won't be 0. It is non-zero.
Okay, non-zero, that much we agree on. But
so Vy into Q by I is equal to 2R.
all right. So again, we are looking at this kind of a cross section. And let me write the thing in green now. Okay. So the Vy is acting upward or downward? You see Vy expression, Vy is acting downward.
Downward.
Okay, Vy is acting downward. So this is our actual Vy, okay? This is our Vy. So the tau xy due to the Vy will be along the Vy direction only. So this thing will come with a negative sign. Okay, at least we understand that the tau that will appear at this point B will be opposite in sense to the one due to shear. That much we agree on. But what is the value of this QZ?
So 4R by 3 pi into area of that semicircular disc.
Okay, so for the point B, we have to take this thing, this area, this entire area. Now QZ will be 4R by 3 pi. What is this 4R by 3 pi that I have drawn, that I have written?
So distance of center of mass from neutral axis.
Not center of mass, say it properly.
I mean, centroid of the
Of the centroid of this semicircular area from the z-axis. This must be multiplied by the area of this semicircle. Okay. So what is the area of this semicircle?
Pi square by 2.
Yes. So this is your QZ. Again, your IZ is what? That we have already written earlier, but let's write it again. So this thing. What is your T? For this point B, yes. Okay, so T is the thickness of the cross section corresponding to the point which is under consideration. So this is the thickness. So this must be twice R. That's it. You know the value of V. Please, we have to be careful here. You have to put the mod here, okay? Because you have taken this sign by considering the actual physical scenario. So it's like this. That's it. But job is not yet done. We have to think about the tau xy, tau xz also. Just think about it. As far as the shear forces are concerned, you have only the Vy. You do not have any Vz in this problem. Okay, in the next problem, the question number 16, you will think about there and then there, but Vz is 0 here. You only have Vy. So corresponding to Vy, you certainly will not have any tau xz. So the shear stress due to the shearing formula, that is not happening here. What about the contribution due to the torsion?
So we already took the contribution due to torsion, and it is not in.
Yeah, it is not in the z direction. That much we are sure about. So overall, this is going to be equal to 0. Okay, so you see the situation is very, very sensitive to the directions you are considering, which things are contributing where. So okay, so earlier also we thought explicitly about those things and we figured it out for the part A, for the point A, and for this point B also we thought explicitly about these things. So you see in the point A, they were contributing separately. The shear force, the shearing formula and the torsion formula, they were contributing separately in the separate directions. Okay, one was in the y direction, the other was in the z direction. But because point B is like this in a separate location, the shearing formula and the torsion formula, they are contributing in the same direction. Okay, so once you do a few problems, then these kinds of things will start to become clear to you. Okay, and the next problem is a good opportunity for you to do that. We will do this. We'll nevertheless do this, but you try this on your own also. Okay, very similar kind of thing, but here you really have to think in terms of 3D equilibrium, because this is a proper 3D. You have to start out from a proper 3D equilibrium scenario. Okay, consequently, you will have a more rich set of things to consider when evaluating the normal stresses and especially the shear stresses. Okay, so I'm at the end of my period now. Thank you very much. Class is officially over. If you want to ask something, I'm here for a few minutes more. Thank you, everyone. You can go to your next class, okay? Or take a 2 minutes break or something.
Thank you, sir.
Thank you.
Excuse me, sir.
Yes.
Sir, I was having some doubts, sir, in this question.
I cannot hear you. Please speak a little bit louder.
Sir, I have some doubt in this question. Is it audible, sir? Now.
Yes, you're audible.
Sir, what is the physical cause of this 20 Newton meter movement?
What is the physical
Cause means who is generating this 20 Newton meter movement?
What is the purpose of a drill?
Oh yeah, sir. Means the motor is generating this 20 Newton meter. So
Absolutely.
yeah, sir. So if we consider the whole this machine as the system, then the reaction of this 20 Newton meter movement will also be in this system only. So why we are representing in this body, means free body diagram.
I'm not getting you.
Hello, sir.
Yes.
So the reaction of this 20 Newton meter will also be present in this body only. So it is not an external movement. So why we are taking?
Oh, I think I've understood what you are saying. So ideally, so for your free body diagram, we should have taken only the drill bit.
Yes, sir. That is it.
Taken only the drill bit here. Then this the torque due to the motor, which is somewhere present here, that would have been like this, or maybe ulta. Okay, like this, and then this force would still be present, but it would be present in a transmitted sense here. The effect would have been the same, absolutely. Whatever values of the mz we are obtaining, we would still obtain that.
Yes.
Its sense. Okay, so how do I depict this? Okay, so maybe just with a line of action, something like that. So this is somewhere here, no? Something like that.
Okay.
And then whatever we have drawn here, you are absolutely right about that. Okay, it doesn't make any sense to draw this entire thing and then also to consider the torque and the reactions like that.
Okay, sir.
Yeah.
Thank you, sir.
Who asked that question just now? Did he leave? Okay, I'm logging out now.